everyone. We're going to look at the Hall voltage derivation today. But before that, we're going to understand how Hall voltage is created and what's the process behind the derivation of the formula. So let's assume that we have this semiconductor material. And initially, if I were to apply voltage here, I can say that this is the positive end and this is the negative end. And according to the conventional current, we know that the positive charge flows from this positive end to this negative end. So I say that initially when voltage is applied, all my positive charges, they travel from this positive end to this negative end, and this just keeps on occurring, and they just travel in this direction all the way to the negative end. Now, what if we put this semiconductor material into an external magnetic field? And I'll just quickly draw that magnetic field. So if we place that in a uniform external magnetic field, one thing that you need to understand is determine where the direction of this magnetic field. In this case, it's going inside the page. So when I get this, when I place this semiconductor into an external magnetic field, now what will happen is that now when a positive charge comes in, it's not going to travel in this direction anymore. Why? Because we have studied that when you place a current carrying conductor into an external magnetic field, they are going to experience a magnetic force. Now, how do we determine that magnetic force? That magnetic force can be in this direction, it can be in this direction as well. So what we will do for that is use Fleming's left hand rule. Fleming's left hand rule. So Fleming's left hand rule says this is my force, this is my direction of magnetic field, and this is my current direction. So you can learn it as FBI for your understanding. FBI. So this is the force. All of them are 90 degrees to each other. So we have FBI. So now when you we need to determine the direction of the force. We know that this is within the page. So when you go within the page and we know that the current is going in this direction, you will know that the force is acting in this direction. So we know that the positive charge, they will move here. So when the positive charge, they start moving here, they're no longer going a straight path. Instead, they are experiencing a force in the upward direction. So whatever positive charge is coming from this end will just keep on accumulating up. Now if they keep on accumulating up, then obviously the negative charge is going to accumulate in this direction. Now, after a while, when there's enough accumulation of this positive charge and then there's negative charge, let's assume we get another positive charge. So a new positive charge entered. Now there are two forces that will be acting on it. Why? Because initially we knew that there was an external magnetic field which was exerting a magnetic force, and now we know that this accumulation of charge has resulted in an electric field being set up. Electric field. So this was a magnetic field, now an electric field has been set up. So this charge is now going to experience two forces. Number one, the electric field, and number two, this external magnetic field. Now we have to determine which one it's going to choose. And how do we do that? We know that if it goes up, it's going to repel here. So ideally it should be going in this direction according to the electric field, because it's going to get attracted by these negative charges. But at the same time, we know that it's experiencing a force upward by the magnetic field. So that's a story of whichever force will overpower, it's going to go in that direction. Now there will be a point where the upward force becomes equal to the downward force. We know the upward force that was acting on it was the magnetic force, which I'm going to write by FB, and we know that the force that's pulling it down are these negative charges which are set up in the electric field, so that's going to be an F. There will come a point when these two forces, they become equal. What will happen in that case? In that case, we will say FE is equals to FB. The electric force is equal to the magnetic force. Now, what is electric force equals to? The electric force is equals to QE. These are the formula that we learned back in electricity chapter as well, that electric force is equals to Q into E, where E is the electric field. Electric field is F over Q, so F is E into Q equals the magnetic force. Now, how do we know which magnetic force formula to use? We know we're looking at this single charge right now, and when we have to take a look at one single charge, the formula to apply is QVB, where this is the charge, this is the drift velocity, and this is the magnetic flux density. Now you can see we can easily cut Q out. I am left with E is equals to VB. Now what do? We have to find out what this is equal to. We are assuming that a uniform electric field has been set up. So once we assume that a uniform electric field is set up, there is this one particular formula for the electric field that is just specific to uniform electric field, and that formula I will write here, that is E is equals to delta V divided by distance. This formula is only applied to a uniform electric field, and we are assuming that a uniform electric field is applied here. So we have the delta V and the distance, and that distance is right here, it's this distance. So I can simply replace E with delta V divided by the distance, and that is equals to VB. Now, what's V? That's the drift velocity. Is there any formula that comes to my mind when I look at these charges below? Yes. One formula that comes to my mind is I equals A N V Q. Now this is the current in a current carrying conductor, the current flowing in the current carrying conductor. And so I have V here as well, I have V here as well. So if I can replace V with this somehow, what I'll do is I can make V the subject of my equation, and I'll get I over A and Q equals V. Now I can simply replace V with I over A and Q, I, and now that will get multiplied with B, I, B over A and Q. Now let's simplify it even further. What's area equal to? This is a cross-sectional area. If this is the distance, this is the thickness, we can say, so cross-sectional area is, if I were to cut out a part of this, I will get this distance and this thickness as my area. So it's D So now I'll have delta V over D equals IB dt and Q. Now, can you notice something common? Yes, I can see a D here. I can see a D here as well. They cut out. I am left with delta V equals IB over T and Q. And delta V is my voltage, so I can write delta V as VH as well. So I can write this as VH as well to denote that this is hall voltage. And I got IB over NTQ as my formula for hall voltage. And this is it for the derivation of hall voltage formula.